Hello, welcome to mensuration questions and answer, solid shapes, surface areas and volumes. So we shall look at some questions on surface areas and volumes of solid shapes. The first one says a cylindrical pipe 50 meters long with radius 7 meters. So let's bring out the parameters. Radius 7 meters, length of the pipe 50 meters. So we have a cylindrical pipe of radius 7 meters and length 50 meters. We want to find the total surface area. So total surface area of cylinder is 2 pi r squared plus 2 pi r h. So the length of the cylinder basically is the height. So let's work that. Now, we need to take note that the answers are left in terms of pi, so that's why you can see pi among the options provided. So this will now be equals to 2 pi radius squared, that's 7 squared, plus 2 pi r h. 2 times pi times radius, still 7, times height is now 50. So let's see what we get from there. 7 squared is 49, 49 times 2 is 98 pi, plus 7 times 50, that's 350, times 2, that's 700 pi. So we have 700 pi plus 98 pi. That's basically 798 pi cm squared. Okay, that's 798 pi cm squared. Now, but the formula I've used here is for when both ends are closed. So here we are told that one end is opened. One end is open, so we need to take note of that. One end open. Okay. So it means the formula becomes pi r squared, because one of the circles will have been removed. We have explained that in our previous lessons. So one of the circular parts is removed, so that becomes pi r squared plus 2 pi r h. So we can have pi r squared plus 2 pi r h. So we calculate these two, that's 49. So that's pi radius squared, pi 7 squared, that's 49 pi. So 49 pi plus 700 pi, that's 749 pi, since one of the ends are opened. 749 pi cm squared. Let's check the right choice. So option D, total surface area for cylindrical pipe open at one end, cylinder open at one of the end. Okay, that's quite easy, straightforward. Move on, let's move on. A solid metal cube of size 3 centimeters. So let's start with the cube. Let's get the volume of the cube. Volume of the cube is straightforward, L cube. The side of the cube, they are all the same, so that's 3 by 3 by 3. That's 27 cm cube. It's placed in a regular tank. So we place it in a regular tank of 3 by 4 by 5. Okay? So that looks like a cuboid, since cuboid is rectangular tank in that instance. So we can find the volume of that. sorry, the first one here is a cube. So the other is a cuboid, place this inside. Since the length, the dimensions are not the same, 3 by 4 by 5, so we can say volume of that is LBH, 3 times 4 times 5, all dimensions are in centimeter, that's 60 centimeter cube. Okay. What volume of water can the tank now hold? Okay, so the basic idea is the small cuboid will have taken a part of the, will have taken a space from which water can stay from the rectangular tank. So if we get the entire volume of the rectangular tank minus volume of this small cuboid, since water will not be inside this small cube, minus volume of this cube, we get the volume of the parts that water can take. So this is the part that water will take. So this part now is volume of entire cuboid minus volume of small cube. So volume of entire cuboid, so the part water can take, volume of water that can now, that the tank can now hold. So volume of water is now 60 minus 27. All is cm cube. So that's 60 minus 20, 40 minus 7, that's 33 cm cube. Okay, let's move on to the next one. Calculate the volume of cuboid. Okay, so we have the length, breadth, and height. That's straightforward. Volume of cuboid is LBH. That's 0.76 centimeters, 6 centimeters, 2.6 centimeters by 0.82 centimeters. So we have 0.76. So we just multiply the 3. 0.76 by 2.6 by 0.82. So we have 1.62 cm cube. 1.62 cm cube. So that's question 1 to 3. Let's move on to question 4. A cylindrical tank has a capacity. Capacity simply means volume. So this is volume, 6160 meter cube. What is the depth? The word depth simply means height. If the radius is 28, so radius is 28 meters. So volume of a cylinder per r square h, volume is 6160 pi 22 over 7, radius is 28. We're told that the base radius is 28, so radius square, that's 28 times another 28 times height, depth. Okay, depth is the height. What is the height? So that's what we're required to find, the height, which is the depth. Let's call that h. Okay, so this is simple mathematics we're going to do. So let's kind of do a cross multiplication. We have 6160 times 7 equals to 22 times 28 times 28 times height. From there we can easily obtain the height. .60 times 7. We multiply 6160 by times 7 and we divide it by 22, 28 and 28. That's 2.5 meters. So the height is 2.5 meters. Just a simple substitution and the answer is out. So let's move to question 4. The figure is a solid with trapezium PQRS as its uniform cross-section. Find its volume. So we have this solid, and we're about to find the volume. So So we have PQRS as a trapezium. That serves as a cross-sectional part. So this is cross-section. Similarly, we have something like that behind, So it's as if we have trapezium, two trapezium, and the distance between the two trapezium is 8, 8, 8. So the 8 repeats itself, 8 meters, 8 meters, 8 meters. So the distance between the cross-sectional area must be the same. That's 8, 8, 8. So how do we get the following? So fundamentally, the shape is a prism. So volume of prism is cross-sectional area times h. H is the distance between the cross-sectional area. So we could identify that h is actually equals to 8 meters. So h is 8 meters. So the idea is the cross-sectional area are two shapes fundamentally the same that appears at the extreme end. The basic idea is the trapezium we see here is like the same trapezium we see here, and the distance between them is 8, 8, 8. That's the height. Okay, so that's the basic idea there. Now let's first start by finding the area of trapezium. That will serve as a cross-sectional area. So that's area of trapezium, half into a plus b times height. That's half into a. Okay, that's 6. Since this side is 6, obviously this side is 6. So 6 plus b, this is 11. Then the height will be the distance between them, that's 12. So half into a plus b bracket height. Here is a, so this is b, and this is height. Okay, so that's fundamentally half. 6 plus 11, that's 17. So the area required is 17 times 12 divided by 2. So that's 102 cm, okay, not centimeter, this time around meter squared. So the required volume of the prism is 102. We have identified the height to be 8, or the distance between the two cross-sectional area. So that's now 102 times 8. Okay, so that's 102 times 8. The answer comes out in meter cube. 816 meter cube. 816 meter cube. Okay, let's move on. That's question 5. Let's go to question 6. Okay. Okay, so question 6. Find the total surface area of a cone of radius 2√3 centimeters, slanting height 4√3 centimeters. Total surface area of cone. So total surface area of cone is curved surface area pi r plus area of the base pi r squared. So we have the radius 2√3 centimeters, and we have the slanting height for the cone is L, that's 4√3 centimeters. So we can use this parameter to figure that out, and the answers are in terms of pi. As we can see among the options provided, all answers are in terms of pi. Okay, so pi, we have pi times radius 2√3 times slanting height 4√3 plus pi times radius 2√3 squared. So So we have pi 2 times, okay, that's 2 times 4 is 8, root 3 times root 3 is square root of 9, which is 3, plus 2 square is 4, root 3 times root 3 is 3, that's 4 root 3, 4 times 3, we square 2, we have 4, the square of the square root of 3 is 3, so 4 times 3 times pi. So 8 times 3 is 24, so we have 24 pi, plus 4 times 3 is 12, 12 pi. That's 36, obviously, 36 pi. Total surface area is pi centimeter squared, 36 pi centimeter squared. Okay, that's question 6. Let's proceed to question 7. Now this is a question on cylindrical pipe. Volume of metal used in making the pipe. Find the volume of metal used in making the pipe. So volume of material used in making cylindrical pipe is pi L into R plus R, R minus R. Okay, let's see. If a metal pipe 10 centimeters long, so L is 10 centimeters, has an external diameter 12 centimeters, so big R is 12 centimeters. That's external diameter 12 centimeters, and thickness of 1 centimeter. So thickness, fundamentally we know that thickness is external diameter minus internal diameter, or we say external radius minus internal radius. So external diameter is 12. So let's say external radius will be 6 centimeters. So let's find our way. So thickness is 1 equals to external radius, that's 6, internal radius R. So 1 plus R is equals to 6. So R is 5. R equals to 5. So that means internal radius is 5. Internal radius 5. External radius 6. Internal diameter definitely corresponds to what? 10. Okay. So let's get the volume of metal used in making a pipe. V equals to pi. The length of the pipe is 10 centimeters. Observe that they must all have the same unit, centimeters. Okay. External radius 6 plus internal radius 5 times 6 minus 5. So this is 10 pi. 6 plus 5 times 11 times 6 minus 5, 1. That's 110 pi. Volume of material, cm cube. Volume is 110 pi cm cube. Let's move to the last one there. Okay. Question number 8. Okay, question number 8. Here we have a composite solid. Oh, volume. So volume is straightforward. So volume we just add up. Now what are the composite solids? Let's identify them. We have hemisphere and we have cone. Let's identify their parameters. For the cone, the height of the cone is 6. As you can see here, height of cone 6. Then the cone has a base radius. Cone has base radius 3 centimeters. Cone has base radius 3 centimeters. Now, since this is a composite solid, the base radius of the cone will serve as the radius of the hemisphere. Very important. Base radius of cone serve as radius of hemisphere. Find the volume of composite solid. Volume of composite solid is very straightforward. It will just be volume of all the solids involved. Just add up the two shapes, add up their volumes. So that can only be done when we are calculating volume. So that's volume of cone plus volume of hemisphere. Volume of cone is 1/3 pi r squared h. Okay, so let's do that. Plus volume of hemisphere is half of the volume of a sphere. That's 2/3 pi r cube. Okay. Now volume of cone 1/3 pi radius of cone that's 3 square, that's 3 times 3. Height of cone 6. Volume of hemisphere 2/3 times pi. Radius of hemisphere. Hemisphere and cone have the same radius. Solid are composite as shown in the diagram. So radius of any cubic power, that's cubic power, that's cubic power, that's cubic power, that's 3 times 3. Definitely we have cancellations. 3 cancels 3. 3 and 3 takes care of itself. So here we have 18 pi. 6 times 3, we are left with 18 pi there. Plus, here we have 339 times 2, 18. Plus another 18 pi. 18 plus 18, that's 36 pi. So we are finding composite volumes. CMQ. 36 pi CMQ. 36 pi CMQ, option B. So volume of composite solid can be very straightforward, and we have that. What about if we have a question where we are required to find total surface area of this composite solid? If we want to find total surface area of the composite solid we have here, just cover this solid with a piece of cloth. It will cover the curved surface area of the cone, then it also cover the curved surface area of the hemisphere. So in that instance, we use pi RL for curved surface area of cone, and we also use 2 pi R square for curved surface area of hemisphere. So that might involve us finding the slant height of the cone. That will involve us to find the slant height of the cone. Then the slant height of the cone can be obtained by using Pythagoras theorem. This is a right angle triangle. Then this will be the hypotenuse, and we use L square, the square of the slant height, equals to R square plus H square. So we can get the slant height. So we use pi RL plus 2 pi R square. That will give us total surface area of this composite shape. But for volumes, we don't have problem. Just add up volume of Mr. A plus volume of Mr. B. Thank you for listening. I'll see you in my next lesson. Bye.